All right, so this is instruction for CP chemistry on gas laws. Now, you guys have been out for a few days, but before you left, you learned about one gas law, and we're going to learn about 1, 2, 3 more gas laws today. But they're all solved in exactly the same way, using the same methodology as the gas law you've already learned about. Let's talk about these gas laws. I'm going to lay them out for you, and I'm going to show you how to solve problems with them. The gas law you already learned about was Boyles Law. And we said that Boyles Law means that if you multiply pressure times volume, no matter what the pressure or volume is, you change the pressure, the volume is going to change. They respond to each other so that you always get the same answer. And the lab that we were supposed to do actually showed that. You could actually multiply the pressures and volumes that we collected in the lab, and we'd always get virtually the same answer. Now, this class didn't get a chance to do that lab, but that's what you would have gotten. Now, there's a couple things that matter here. Pressure and volume are the only two things that are going to change. You have to keep the amount of gas the same. That is, you can't let any extra gas molecules in or out, and you can't change the temperature for this to work. Now, it also means that if you have an initial pressure and an initial volume, and that equals K, as long as you don't change the temperature or the amount of gas, if you change volume, pressure is going to change, and those are also going to equal K. Okay? And if this statement is true, and it is, okay, that's what we would have seen in the lab, then it's also true that that P1 times V1 is going to equal P2 times V2, because if two things are equal to something, okay, if they're equal to the same thing, then those two things are always equal. So P1 times V1 equals P2 times V2. Okay, so that's Boyles Law. Then we're going to learn today about Charles' Law, in a rudimentary sense anyway today. And what happens with Charles' Law is that if you have a volume of a gas and a temperature for that gas, that ratio, it makes a ratio like this. Now what this Boyles Law means is if pressure goes up, the volume has to go down in order for pressure times volume to equal a constant. But what Charles' Law means is that if volume goes up, the temperature also goes up. If temperature goes down, volume goes down in order for this ratio, this division problem to always equal K. Well, if this is true, then V1 over T1, an initial volume and temperature, if you change, that's going to equal K. But if you change volume or you change temperature, as long as you don't change the pressure or change the amount of gas, if you keep those the same, then and if you change the volume or temperature, the other variable is going to change as well to always equal K. All right, so that means that volume over temperature equals volume over temperature. Now, when we have these 4 variables like this, if we know 3 of them, we can find the 4th one. That's something you should already know from math. And that's the same for either one of these 2 equations. Now, this kind of relationship here is called a direct relationship. It means that if we have a graph of this, it goes up like this. It goes in that direction. As long as the volume is going up, the temperature is going up, or depending on which side you've got, which one of those is your independent variable. Boyles' Law has an inverse relationship. If pressure goes up, volume has to go down, so you end up with this curve. Okay? So, then there's a law that I'm going to tell you about, but you don't really have to know in this class. It's not in the state standards in high school chemistry, but it's called Gay-Lussac's Law. These are 2 different people. They just happen to have discovered the same relationship at about the same time, so they're both given credit for it. And both these researchers found that if I have a pressure and I divide that by temperature, that's always going to equal a constant. So it's the same kind of relationship as this. So all of these terms, all of these laws only deal with, so far anyway, two variables. So, and what it tells us is as long as we keep everything else the same, we control all the variables except pressure and volume, then this works. So the number of moles of gas, the number of atoms of gas can't change for Boyles Law, the temperature can't change with Boyles Law, and as long as that's the case, this pressure-volume relationship works. For Charles' law, we're only looking at volume and temperature, so we can't change the pressure for this to work, nor can we change the number of moles of gas. So as long as you don't change the number of molecules of gas or moles of gas, and you don't change the pressure, Charles' law works. In Gay-Lussac's law, the volume can't change. Pressure and temperature change, but the volume can't change, nor can the number of molecules or moles of gas change for this to work. Well, this works out kind of like the same thing. If pressure over volume, pressure over temperature equals K, and if we change the pressure or we change the temperature, the other variable changes in the same direction, so they always equal K. Well, that means that some second pressure and some second temperature is still going to equal K. K is a constant. We said this before you went on spring break, but just to remind you, K is a constant, some constant for this relationship. Well, if this term right here, P over T, equals K, and this second P over T equals K, well, then that means this term and this term, P over T1, P1 over T1, P2 over T2, those two are equal. So we've got P1 over T1 equals P2 over T2. All right. And one more gas law. Well, no, before I do that, I'm going to combine these three. I'm going to go to the combined gas law first. So if we put these laws together, we're going to put them together. We're going to combine them. We call it the combined gas law. So in this case, what we're looking at is, what if we are changing pressure, volume, and temperature? Well, you put all those together, and you get this relationship, that pressure, volume, and temperature, put together in this fashion, equals some constant, which means it equals, if we change any one of these are going to, the other variables are going to respond in a way that keeps those equal, or keeps those equal to some constant. And so we're putting these three together to get this combined gas law. So we're calling it the combined gas law. All right. So what we're doing is taking all three of these right here and putting it together to make this. Well, we're going to put this together now with another gas law. Only I'm going to kind of back up a little bit, because what we're going to look at is just this relationship. P times V over T equals some constant. Well, that just means that these three things here, this one, and this one are all added together. Now this K here is not the same numerical value as this K. They're a constant, so for these three variables you get a constant. For these two variables you get a different constant. For these two variables you get a different constant. For these two variables you get a different constant. But it's nevertheless a constant as long as you're only dealing with those variables. But I'm going to start with this right here, and I'm going to introduce you to something called Avogadros' hypothesis. You may remember Avogadro. He's the one for which we name Avogadro's number. And Avogadro's number states that 1 mole of particles of anything is equal to 6.02 times 10 to the 23rd particles. I'll write that out for you here at the bottom. Avogadro's number. Raise it up so you can see it. This is just a reminder. This came from the last unit. We're now in Unit 7. This is from Unit 6. Avogadro's number says that 6.02 times 10 to the 23rd particles of anything equals 1 mole of that thing. Okay, and that's something you have to memorize. You have to know this number. You have to know this relationship. But Avogadro's hypothesis is what led to the discovery of this number. Avogadro didn't actually find this number. That was found by researchers many years later. What Avogadro figured out was that that the volume of a gas divided by the number of particles of that gas. In our case, we're talking about moles. N stands for moles, just like this equals a mole down here. N is the number of moles of gas, and the volume have a relationship in which they equal some constant, which, using the same mathematical concept we used up here, if that's true, then V1 over N1 equals K, and V2 over N2 also equals K, and therefore V1 over N1 equals V2 over N2. All right? Now you don't have to actually know this. Okay? That is to say, I won't ask you a question on a test that says, show me Avogadro's hypothesis. I'll pick out Avogadro's hypothesis from these choices. Nor will I ask you to pick out Gay-Lussac's law. I'm just wanting you to see where we get these other laws from. Now, the laws you do have to know in this class are Boyles Law, Charles Law, the combined gas law, and one more law we're going to talk about. Boyles Law, Charles Law, combined gas law, and one more law we need to talk about. Now, you need to know also that Boyles Law means this, and it means this. You need to know that Charles Law means this, and it means this. And that the combined gas law means this and this. Okay, you don't have to know Avogadro's hypothesis. But here's the reason I want to show you Avogadro's hypothesis is because if I take this statement right here, this equality statement, this equals statement, this mathematical statement, and I put it together with this, okay, this version of this statement. When I put them together, so I've got volume in both of these problems, okay, so it's going to be pressure times volume. I'm not going to restate volume here, but I'm also going to put that put this over temperature as I have it in this, and I'm going to put this volume over number of moles here. Well, if this relationship equals a K and this relationship equals a constant, then the combination of these relationships is going to give us a new constant. However, this constant is so important that we give it a special symbol. We're not just going to leave it alone and say that's K. We have a special constant that we're going to call R. Now, this is the basic idea behind where we get something called the ideal gas law. Okay? In certain parts of the world, including Britain, they'd call it the perfect gas law. So if you ever hear perfect gas law, it means the same thing. Well, ideal gas law is not usually written like this, but we can mathematically get the same thing. I'll show you what I mean by that. Let's put PV over Tn. Now, temperature is always in Kelvin. We learned that. We learned about Charles. Well, I don't know if we've learned that in this class or not, but I'm going to tell you that now. Temperature has to be in Kelvin. So if I give you the temperature in Celsius, you have to convert. In a minute, I'll show you how to do that. All right, so we've got this. I want to rearrange this so I don't have T and N over as a fraction on the bottom. So what I'm going to do is I'm going to multiply both sides of this equality by the same thing. And if you remember, as long as you do it to both sides, that's an allowed mathematical operation. If I multiply this side by Tn, Kelvin temperature times the number of moles, N stands for the number of moles, and I'll do the same thing on this side, Tn, that's allowed. It's allowed that you can do that. As long as you do the same mathematical operation to both sides, the equality is still valid. Well, just to make sure we're clear on what we're doing, let's put that over 1. So let's see. On this side then, t and n disappear because they're exactly the same, top and bottom. Any variables you have on the top that are the same as those on the bottom, that are both on the same side of an equality statement, you can cancel those out, just like you can cancel x's and y's in algebra. Well, let's rewrite the problem then. Now we've got just PV here. Well, PV over 1, that's the same thing as PV. I mean, 2 over 1 is just 2. 5 over 1 is just 5. So when you divide by 1, it gives you the same thing. So we can now say this is PV on this side. And on this side, we've got R, because these are all over 1. We can just, for the same reason, we can just say R times T times N. Well, the way it's actually usually written is not R times T times N. We can rearrange these. You can put these in any order you want to. And so the way you usually see this written is PV equals N R T. And that's the classic statement of the ideal gas law. So you have to know the ideal gas law. Okay? You have to know it. Now, like I said, R is so important that it has a special name. And if you will get out your test references, if you don't already have your test references out, I want you to get those out now. I want you to turn to the first page and look in the bottom right-hand corner. Okay, and you will see R. Now down here, instead of the ideal gas constant, it's called the universal gas constant. That's fine, because there are cases where we don't use a gas in the classic sense that we're going to use it here. So that's why it's called the universal gas constant. It's used in a broader set of problems. The versions of R, and there are 6 versions of R, they're all equal. They're the same number. Okay? They're just written differently because we're using different units of measurement. Okay? And we've converted this number to this number because we've changed the units of measurement here. Just like if I have 1,000 milliliters, well, I can't say 1,000 milliliters equals 1,000 liters. You have to convert. 1,000 milliliters equals 1 liter. Well, the same thing here. We've done a conversion. We don't actually use these 2 versions of R. I list them here just because I want you to know that they exist. But these are more used in calculations of energy, and we won't actually use them in this class. But I wanted to introduce you to the term joules and calories, which come up in the very last unit of this class. The 4 versions of R we might use are these 4. This one, this one, this one, and this one. And the only difference between these is the unit that's used to measure the pressure. Atmospheres, ATM, that measures the pressure. Millimeters of mercury, that's mmHg, that's the measurement of pressure. It's a different measurement of pressure than this one. kPa, it's a different measurement of pressure than millimeters of mercury or atmospheres. And torr is a different unit of measurement, although it is exactly the same measurement unit as millimeters of mercury. It's just called torr in certain circumstances. In other circumstances, it's called millimeters of mercury. So we've got 1, 2, 3, 4 gas laws that we have to know. And all those gas laws are used in exactly the same way to solve problems. So in the next video, we are going to start working with those problems.